Here is a combined summary of the 2 pages from the research paper. The authors propose a novel approach for understanding the periodic structure and semantics of motion datasets, independent of the morphology and skeletal structure of characters. They present a phase manifold consisting of multiple closed curves, each corresponding to a latent amplitude, learned using a vector quantized periodic autoencoder, VQPAE. This manifold enables timing and semantics alignment between motions from different characters, without any supervision or paired data. The VQPAE decomposes motions into a 1D phase and discrete amplitude vectors, forming a disconnected 1D manifold where each component is an ellipse corresponding to a discrete amplitude vector. The possible choices of amplitudes are learned through vector quantization, similar to a clustering process. The discrete amplitude vectors serve as a narrow bottleneck to regularize unsupervised learning of semantic motion clusters. The authors demonstrate the capability of the phase manifold for motion alignment, retrieval, transfer, and stylization. They learn VQPAEs from both a human dataset and a dog dataset with a shared codebook, and show that the learned embeddings are both timing and semantics aligned between the 2 characters. This highly structured and aligned phase manifold opens up new possibilities for motion data organization and integration with existing motion synthesis pipelines. The key contributions of this work include a novel phase manifold designed for both timing and semantics alignment, demonstrating the use of narrow bottlenecks and intrinsic structure of motions to achieve alignment among heterogeneous datasets without supervision, and applications with an improved motion matching framework on the phase manifold for motion retrieval, transfer, and stylization. Title: Walk the Dog. Cross-Morphology Motion Alignment via Phase Manifolds. The authors present a novel method for motion alignment and retargeting across different characters, leveraging the concept of phase manifolds. This approach is based on the idea that motions can be organized by their periodicity and phase, allowing for a more efficient and effective way to align motions between characters. The authors first introduce the concept of a disconnected 1D phase manifold, which is constructed using an ellipse embedded in R(D). This manifold is parameterized by a 1D phase variable and a vector amplitude, with the amplitude being chosen from a finite codebook. This construction allows for a latent space that consists of a collection of ellipses, where each ellipse represents a class of motions with similar semantics. The authors then describe their vector quantized periodic autoencoder, VQPAE, architecture, which is used to learn the embedding of motions from one dataset. The VQPAE consists of an encoder that predicts the amplitude, phase, and frequency at the center frame of a short input motion sequence. The phase is then extrapolated linearly with the predicted frequency to the whole sequence, and the embedding is calculated using the predicted amplitude and phase. A decoder is used to reconstruct the input motion sequence from the predicted embedding. The authors also discuss the loss function used to train the VQPAE, which includes a reconstruction loss and a vector quantization loss. The reconstruction loss ensures that the reconstructed motion sequence is close to the original input, while the vector quantization loss encourages the amplitude to be chosen from the finite codebook. Overall, this paper presents a novel approach for motion alignment and retargeting that leverages the concept of phase manifolds. By organizing motions based on their periodicity and phase, the authors demonstrate an efficient and effective method for aligning motions between different characters. Here is a combined summary of pages 5 and 6 of the research paper. The authors propose Walk the Dog, a method for cross-morphology motion alignment via phase manifolds. They learn a common phase manifold among multiple VQPAEs, vector quantized product of asymmetric experts, by sharing the codebook A and optimizing a loss function that combines reconstruction losses and vector quantization loss. To ensure that the codebook is utilized effectively, they adapt a reinitialization technique from Jung and Vidaldi, 2023, to reinitialize less frequently used entries in the codebook. The authors demonstrate that their method can learn a common phase manifold with only a shared codebook A and no additional supervision, unlike existing methods that require partially specified skeletal topology correspondences and additional implicit supervision. They use the learned phase manifold to model different character topologies, including biped and quadruped, without extra class-specific designs. The authors also propose frequency-scaled motion matching, which solves the problem of timing and semantics misalignment in motion matching. They perform matching on a fixed number of cycles instead of a fixed number of frames, allowing for more responsive and smooth motion transfer. They demonstrate the effectiveness of their method on several datasets, including dog, human locomotion, and mocha, and show that it can be used for improving motion matching, motion transfer, and motion stylization. In the evaluation, the authors examine the average pose at each point of the manifold to verify its alignment effect and propose training a small MLP for each dataset to minimize the pose loss. They also evaluate their method on different settings, including human dog and stylized settings, and show that it is possible to learn a shared latent space for multiple datasets with different characters. Here is a combined summary of pages 7 and 8 of the research paper. The authors present a novel approach to cross-morphology motion alignment via phase manifolds, dubbed WalkTheDog. They demonstrate the effectiveness of their method in retrieving motions at different frequencies from the same connected component, achieving semantic alignment between motions of different characters, such as a dog and a human. The learned phase manifold enables the disentanglement of phase and amplitude, allowing for motion stylization and characterization. The authors also conduct an ablation study to investigate the impact of codebook size and reinitialization of the amplitude on the performance of their method. They show that a larger codebook size improves expressiveness but reduces the percentage of embeddings in the dataset that lie on a shared connected component. They choose a codebook size of 32 for the human dog setting and 64 for the stylized setting based on the results. The success of their simple motion alignment lies in the limited capability of the shallow VQPAE, which prevents large distortions between the motion representation and the latent embeddings, and the design of the compact latent space. The authors discuss the limitations of their current framework, including the requirement for carefully picking the right codebook size to balance between expressiveness and overlap among datasets. Future research directions include automatically learning the size of the codebook, filtering out motions that are not semantically similar, and exploring the possibility of generating new motions from the phase manifold. The authors also acknowledge the potential of training the Peizhuo with other 1D input signals, such as a music dataset, for tightly aligned music to dance generation. This paper introduces WalkTheDog, a novel approach for cross-morphology motion alignment that leverages phase manifolds. It aims to address the challenges in motion transfer between characters with different morphologies, focusing on preserving both the semantics and timing of motions. The authors draw inspiration from various fields, including physics-based character skills, deep reinforcement learning, and image synthesis. They highlight the importance of robust 3D pose estimation and motion in-between with phase manifolds, as well as the role of Fourier principles for emotion-based human figure animation. WalkTheDog is designed to overcome limitations in existing methods, such as deep phase and SAN, which struggle with entangled phase manifolds and unstable adversarial training, respectively. By disentangling phase and amplitude, WalkTheDog can generate motions that combine the semantics from the amplitude input and the timing from the phase input, resulting in more plausible and characterized motions. The paper also discusses the potential applications of WalkTheDog in various domains, including computer graphics, robotics, and virtual reality. It emphasizes the need for further research into motion phase manifolds and their role in enhancing the realism and efficiency of motion transfer algorithms. In conclusion, WalkTheDog presents a significant advancement in cross-morphology motion alignment, offering a robust and efficient solution for transferring motions between characters with different morphologies. This approach has the potential to revolutionize the field of computer animation and beyond, enabling more realistic and engaging character movements in various applications. Here is the combined summary of pages 11 and 12 of the research paper. The WalkTheDog framework employs a phase calculation module to compute the phase manifold, which is crucial for motion alignment. The phase calculation is based on the equations presented by Mason, 2022. Using the entries from a one-channel signal and relative timing to calculate the phase. This approach helps avoid dealing with the fact that the phase is not a continuous parameterization of the phase manifold. The motion matching algorithm, outlined in Algorithm 1, retrieves the motion sequence from the database using phase embedding as the control signal. The algorithm iteratively finds the closest match in the database, measured by the similarity between the pose descriptors, and outputs the corresponding motion sequence. The pose descriptor used is a simple normalized joint position, ensuring a smooth transition between different replays. Inertialization is applied at each transition to maintain a consistent motion sequence. The authors provide an overview of the datasets used in their experiments, including dog, human locomotion, mocha clown, mocha ogre, and mocha princess. The training time varies depending on the dataset size, ranging from 40 minutes to 2 hours and 40 minutes. The network architecture consists of a convolutional encoder and decoder with a shared architecture, as well as multiple MLPs for different tasks, including raw amplitude production, phase calculation, and learning average poses. The hyperparameters used include a learning rate of 1 × 10⁻⁴, batch size of 32, and the atom optimizer. The input feature used is joint velocity in the local coordinate of the character. The authors also specify the hyperparameters used in frequency-scaled motion matching. The paper references various works, including skeleton-aware networks for deep motion retargeting, MoCA, real-time motion characterization via context matching, and periodic autoencoder explanation and addendum, among others.